Here we go. Here's the solution to the single problem in homework number 18. I decided to make my own problem, and this is a good kind of a good engineering skill set to have. Find the mass moment of inertia, something especially because keeping track of stuff that's complicated and solving something in two different ways. These are kind of things that these are like skill sets that we really need as mechanical engineers. And interesting when you're able to find the actual solution to something, and this will be fairly close to the actual solution of this particular problem right here. So here's the SolidWorks result of this rocket ship, right? I guess it's this huge plastic rocket, solid plastic, I don't know. It's just an estimate, and we just made some estimate on some things. But anyway, so I'm your crazy Uncle Steve, and if you're fortunate not to have a crazy Uncle Steve, God bless you, but you know who I'm talking about. He decided he wants to build a rocket, a backyard rocket, and so we want you to help him find the mass moment of inertia about the X, Y, and Z axes, but also about the axes that pass through the center of mass, right? So we have right here at the bottom, right here. For some reason, Y is down here, but Z is the vertical one. It's really because I drew it that way, and then I was like, I don't want to fix it, so I left it that way. So you can see here's the X is coming out of the page right here, and the Y. And here are the different parameters, the different sizes and individual masses. Now I could probably have gotten away with not giving you the masses, and then make you find the volumes and multiply it by the density, right? And that would have given you these values right here for all of them, or fairly close. Our main mission is to do our very best to try to get the answers, right? So you see that the total mass right up here should be 12,665 kilograms. I think right from the beginning we're going to find out that we're maybe just a little off from that. And then the center of mass, the X should be 0 and Y should be 0, and you see the Z should be like 1.95. And then we're going to have these mass moment of inertia. It's going to be these diagonal terms that we're going to try to replicate. And it might be a good idea to do this in Excel as well as doing it by hand. I don't think I asked you to do. I said to ask you to make tables, but I didn't say do it in Excel. But I think it's a good skill set to do it in Excel as well, because I've done many problems like this in my engineering career where I had to create a table for something. Most of the time for me it was like weights and centers of things. Of course there was shipboard things, naval architects. We also need to find the center of the ship, right, and in multiple axes. We also need to get the moment of inertia of area moment of inertia of stuff, so we end up making a lot of tables similar to this. Alright, so I've put together my little sketch of the homework. And this is something I've been asking you to do. It is the right thing to do, but I haven't quite given up. I keep leaving comments like, please write out the problem ahead of time. I know this one was long and involved. So here's our strategy first. Let's get the center of mass. We know we're going to need the vertical center of mass because it's symmetric. All the other centers of mass should be right there. Like the X and the Y should be right here in the center because this thing is axially symmetric. So that's a good thing to check out to start with. And let's see, I'm going to draw the X in here, and maybe I'll draw this out right here. This will be the Y axis, and I didn't include the Z axis right here. So there you go, Z, as the Brits like to say. Alright, so let's find the vertical center of mass, and in order to do that, so that's going to be Z is going to be the summation of all the MI's and all the ZI's divided by all the summation of all the individual masses, right? So let's check this out. Best way to do this, I think, is to make a table. Right? This is the equation that we're using, but we will make a table here. And my first thing to put in here is the MIs, right? And I don't quite know what I will put along this length right here, so I'm going to leave it generic for right now. But we know we've numbered this already. So if you didn't have this pre-numbered, you would start picking out numbers and categorizing the things. You got to be a little careful. I think right now we're going to be okay. When we do the moment of inertia, we might need to have actually sub-breakdowns of these depending on what axis. I haven't solved this problem before, by the way. I'm doing this live. So anyway, we're going to start with part 1, which is this main base right here. Then we're going to go 2, the fuselage I called it, is the nose cone. 3, and there's 3 of them, are the rockets. And then 4 is going to be what I call the rocket connectors, right? So these little guys that are in there. And I don't think I gave you how high they are, like right here. So I'm going to go ahead and assume like maybe that they're going to be halfway up, right? Let's see, are they halfway up? They look about halfway up to me. Okay, that's good. So I'm going to say that H4. And this is also typical of many engineering problems that you will run across. You won't always have all of the dimensions and all of the information, so you'll have to make some assumptions. So I didn't give you H4. I probably should have. All right, so I'm going to keep looking at the time and saying, how long is this going to take me? Hopefully it won't take you that long. So the mass of 1 was simply 9,630, and the mass of 2 is 1,330, and the mass of 3 is going to be 3 times 535, and then also we're going to have 3 times oh, I messed it up already. What? No, I think I wrote this down wrong. I must have copied that down wrong. Nope, I messed up. Well, I'll have to fix the problem. So 1 second, let me pause the video here and fix the problem. Okay, so here it is. I fixed it. It was supposed to be 21.9, right? So there's going to be 3 times 21.9. All right, so let's get those values in. So 535 times 3 is 1,605, and 21.9 times 3 is 65.7. Okay, so we can make a column right here. And I'm going to sum these up. Right. Fix that a little bit. So let's see, Adam in 1330 plus in 9630 plus. So I get 12,631. Let's call it kilograms. Okay, now we need to find the z of each of these, right? We could even say it with the z bar, right? It's the location of them. Well, some of them are going to be pretty easy to do. Some of them we might need to. Yeah, I think most of them will be easy to do. It's actually the nose cone is the only one we're going to have to look up, find out. So this one is just going to be 1/2 the height of the thing, right? So the height is h1. So we'll just take h1 and divide it by 2. So h1 is 3.66 divided by 2. And I'm only using I only gave you 3 sig figs there, so there's already going to be a little bit of a error kind of built into it, but that's just making excuses. So that's 1.83 meters. This one is going to be to the oh, we need the nose cone. So we'll look that up in our textbook right here. So let's see. I think. Okay, so there's probably going to be two different places depending on where you are in the two different places depending on whether you have the single book right here or whether you have the double book, right? If you have statics and dynamics combined. I think they have, in the dynamics alone, standalone, there's an appendix B, but I don't think they have it in the big, I don't think they have those appendices. No, they don't in the larger book, right? So in the larger book, I think we're going to be in, I think it's like, oh, I just flipped to it. It's like chapter 5, and there's various things in here. I'm trying to find if they have the same table. I don't see it in the standalone book. It's interesting. Okay, so let me show you what I'm talking about. Here is in the appendix B, right? So this is table B9. It's benign, right? But I'm looking for the height of the center of this. It's center of mass. And I'm not seeing it, right? I should see, yeah. Maybe back here? I think, they don't have it. Yeah, I guess you're just going to have to live with that. Some books actually used to have it in the cover. Some of the editions of this. Here in chapter 5, is the center of the cone, and they're telling us that it's h/4, right? So that's for a standard cone. You could also look it up on the interwebs. That's what old people say when they're trying to be cool, right? So they say the interwebs. But I just forgot what it was. h/4. Okay, so the height of this thing was 1.52. So let's take 1.52 and divide it by 4, and it almost seems to me like we should like speed up this whole thing. Like I should erase all the gaps because it takes far too long, right? 0.38. I'll go through sig figs, and let's see for 3 for this one. We should have the half of h3, which is going to be the same thing as h4. So h3 was 1.83, right? And so now we're going to have 1.83 and divided by 2, and 1.83 divided by 2 is 0.915, and then this is actually going to be the same value right here, 915, right, for the fourth one. And now what we want to do is let's make another column and just add these two together, right? Not add them together, multiply them together. So this is MIZI, the same thing as we have up here, but we'll just multiply these, and so 9630, 1.83, and 1330.380, and then 1605 and 0.9150, and then our 65.7 and 0.9150. And as I'm doing this, I'm thinking the video is already too long, so what I'm going to do is I'm going to break it up into 2 parts. I'll do this one, and then I'll make, so this will be the center of mass portion of this, and then I'll do another one for the moment of inertia one. And maybe I might even break it into another part where I move the moment of inertia, but I think it's going to be pretty quick for the other one. Well, let's see. Let's just see how that works out. All right, so 9630 and 1.83 and multiply. Oh, I meant to make this longer, right? I accidentally, but I'm going to shove it down here. Okay, so I'm going to stick it inside here and say I got 17,623, right? One nice thing about the Hewlett-Packard calculator is you do your stuff, and I guess most calculators, I could just keep adding the things as I come down. So that's one of the very useful things about the arrangement of the logic of the Hewlett-Packard calculator. So multiply these guys. I didn't give something very big, did I? No. Oh, I made a mistake here. This was just from the height of the, this is simply the height of the cone. I need to take it from the same spot, so it needs to be from the base. So I need to actually add 3.66 to it. So I'm going to add 3.66, and so I'm going to go, let's see, 1.5 divided by 4, and then add 3.66. Boom. Yep. So that's going to be 4.035, right? Remember that we're going to, so I found it just to the base of this, but we need to do it from a common axis, and that's going to be from the bottom, so it needs to be that direction. Okay. So already a mess up. Man, there's so many opportunities to mess up when you have something long like this. So 4.035. But I caught myself because I saw how small the number was. It did, give yourself, lots of sanity checks along the way to try to see if you've, to try to catch your own mistakes. And then do sanity checks at the end just to say, like, I know what this is. I know what's going on here. Now, I'm adding them, I'm accumulating them as I go along in my calculator. So 0.915 times, and so I have a 1,469, and then I didn't leave myself much room right there, and 65.7 times 0.9150 times, all right, so this is a very small 60.12, I guess, right? Add them together, and I end up with 24,518. Now these are kilogram meters, right? You can almost think of them as a moment of mass. It's, instead of a force times a distance, it's mass times a distance. So it's like a mass moment, right? And so when we want to find what the z bar is going to be, it's going to be just as we had this equation up above. It's the summation of all of those, or the 24,518 divided by our 12,631. We're going to have fingers crossed that we're going to get the same number as the SolidWorks, 1.941 meters, because we divided kilogram meters by kilograms. So this is our first part, the first thing we need, and I think the video is sufficiently long. 19 minutes. So we don't really want to go over on this, and we'll break it up into another video where we'll do the moment of inertias here. But yeah, this is our first task, get the center of mass quite often. And then the next tasks we'll figure out what the resistance to rotation is, which is what the mass moment of inertia is. It's got inertia and it doesn't want to rotate, so we gotta calculate that out for Uncle Steve, who wants to fly in a rocket. Maybe Steve will take off into space. Hope.